It's time to get your arrows popping. Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about graphing exponential functions. That's right, you, me, and a whole lot of graphing. That's what's about to take place, so strap on your seatbelt because we have a roller coaster ride of problems to get through today. But first, go ahead and click on that subscribe button, and while you're at it, click on the notification bell so that you can be notified when we are uploading new and fresh content for you. That is right, guys. So go ahead and do that, and we'll dig right in with the content of the video, which will contain parent functions, transformation maps. We will have 6 examples in this video with multiple techniques looked at, and we will deal with different bases in the exponential functions, as well as give you step-by-step instruction on how to graph these functions and then some. Moving on, we have the following exponential functions, the following examples in this video. So go ahead and take a quick view at the different problems that we'll be taking a look at during this video. As I promised, we have 6 examples, and you're looking right at them, people. These are the 6 examples that we will be covering in this video, moving right along. What I want you to know as a foundation is that when you're dealing with exponential functions is that the basic function that you're looking at is this f of x equals to b to the x in black. But there are conditions on this. The base, which is the b value, has to be positive and it cannot equal to 1 in order to be in the format of an exponential function. As long as the format of the function is in this form that you're looking at, then all graphs of this form will pass through the point 0, 1. The x-axis will be the horizontal asymptote, and if b is greater than 1, then the function will be increasing as x approaches infinity, and if the value of b is between 0 and 1, then the function will be decreasing as x approaches positive infinity. All right, so in other words, as x gets larger, gets bigger in value, then the y value will be decreasing in that last case for number 4. And another thing you'll want to keep in mind is that every graph of an exponential function is going to be a one-to-one function. All right, so that's really important, guys. So keep that last part in mind as we continue on and look at problem number 1. So here we have the basic function f of x equals 2 to the x power. And the thing to keep in mind is that your base of the function, in fact, I'll circle it, it is this 2 value right here. That is the base of the function, and that base once again had to be positive. Remember, it had to be positive and it could not equal to 1. Well, definitely this fits the bill because 2 is definitely positive and it doesn't equal to 1. So we have the basic format for our exponential function here, and because it is in this form, we know that the horizontal asymptote must be the x-axis, which is going to be the equation y equals to 0. So that is going to be the floor of our function. And the reason why we know that's going to be the floor of our function, guys, is because just look at the function itself. 2 to the x, there is no mathematical way that we can make this value equal to 0, and there's no mathematical way to make this a negative value, right? So no matter what value that you can plug into x, which can be any real number, by the way, there's no way you're going to be able to generate 0 or a negative value out of this function. It's not possible. So as we look at this function, you should also recognize that there are no domain restrictions. So what do I mean by that? Well, what I mean is that we can plug in any number because we're not trying to take the square root of a value. We're not trying to take the even root of a value like a square root. We don't have our variable in the denominator of a fraction. We're not trying to take the logarithm of this value, nor are we even involving any trigonometric functions. So we have an exponent that happens to be the variable x. However, since there are no restrictions on that variable x, you can plug in any number you wish. And because of that, I'm going to remember something very important, and that is I really love myself a lot. And because of that, I'm not going to be putting in any stupid numbers into this function. In fact, I'm going to keep the numbers pretty simple. And I'm going to generally use the following set of values when I plug in numbers into functions, guys. And that is -2, -1, 0, 1, and 2. So because I'm allowed, because of the domain being all real numbers, since I'm allowed to pick any value for x, I'm choosing to pick these small numbers so that I don't have to be stressed out when I'm either graphing or calculating what these results are. Okay, so we'll be finding out what f of negative 2 is. Well, if we replace the value of x with negative 2, you'll have 2 to the negative 2 power, which gives you 1 over 2 squared as you get rid of that negative exponent, which ends up simplifying to give you 1/4. All right, so anytime you plug in negative 2 into our f function here, then the result will be 1/4. If we find out what f of negative 1 is, well, that's going to be 2 to the negative first power, and if you shift that base down to the denominator, you'll end up with 1/2. If we plug in 0, finding out what f of 0 is, that's 2 to the 0 power. Well, that equals to 1. Plugging in 1, you'll have f of 1, which equals to 2 to the first power, and that result will be 2. Finally, we'll find out what f of 2 is, and plugging in 2, you'll have 2 squared, and that equals to 4. And this is how we can generate points on our graph that we'll be graphing very shortly, guys. Okay, so as we continue, we'll keep in mind our XY chart, which is right here, guys, that I brought from the previous page. Okay, so we have our points that we're going to be using, the X and Y values that we chose, especially when it came to the X values, we chose those values to plug in into our function here. Okay, and of course we have our function at the top, f of x equals to 2 to the x power, and we have a notation at the bottom that the horizontal asymptote is y equals 0. And since many of our graphing problems ask for this information, we'll go ahead and tell them that our domain is all real numbers. In other words, in interval notation is going to be negative infinity to positive infinity, and we'll be making sure that we start graphing with the horizontal asymptote. So this horizontal asymptote, guys, I'm going to show this by using a dashed line on the x-axis. Okay, so we already have identified the fact that our horizontal asymptote is this horizontal line going through the x-axis, and from there I'm going to start plotting points from our xy chart. So the first point I have is negative 2 1/4, so that's going to be about right here. We have a point at negative 1 1/2, got a point right here. We have a point at 0 1, there we go. We have a point at 1 2, right there, and we have a point at 2 4, which gives us a point here. And so if you go ahead and continue this process, if you needed even more points, you could create some. So next we'll go ahead and connect our points together, and from here you're going to get close to 0 but not quite touch 0, guys, and you're going to have arrows on both ends, and this is going to be the graph of your function f of x equals 2 to the x. And with this graph in play, people, it's going to be easy for you to identify what your range is. So the range of this, remember that we never touch 0, but we get increasingly close to 0. So our range is going to be from 0 to positive infinity as you move from left to right on the graph. Notice that this graph is increasing. The values of y, aka f of x, are getting larger because our base was greater than 1, right? So what did we say earlier? We said that as long as that b value was greater than 1, then the graph would be increasing, and it is. So this is it, guys. This is what you want to know. So let's go ahead and red box some of the results that many of your courses may be asking for. So whether you're in a college algebra class or a pre-calculus course, all right, you'll be asked, what is the horizontal asymptote? What is the domain? What is the range? And obviously, what is the graph of the exponential function? So here you go, guys. That was example number 1. Moving on. I would like to remind you guys to please donate to Forbidden Tutoring. There's going to be a donation link in the description box as well as on our About page. This is what helps us produce more and more free content for you guys. So if you're willing to donate any amount, it definitely helps us out as far as getting more videos produced for your viewing pleasure. So if you're able, go right ahead. We'll put it to good use. Thanks in advance. Now we have problem number 2. And in problem number 2, we have g of x, which equals to the quantity 1/2 raised to the x power. Now, once again, it's that value that we have in front of our exponent of x that is going to be the base of the function. In this case, notice that our value of b is between 0 and 1. So in this case, we should expect for the graph for the function to decrease over time. As x increases, the value of y will decrease. It is still the case that your horizontal asymptote will be the x-axis, which is going to be y equals 0. And it's also the case that I'm purposely choosing the following values of x to plug in. I'll be choosing -2, -1, 0, 1, and 2. Remember that these values are not static. You don't have to use these values. This is a personal choice because I love Mr. Whitt. And because of that, I don't want to be stressed out with any other type of numbers to plug in. I want to be able to plug in little bitty easy numbers that are not too stressful on my brain. Okay? But you are free to choose any value of x that you like. Okay, if you want to plug in -3,175 and 2600ths, you go right ahead. I'll be sticking with -2, -1, 0, 1, and 2. All right, so we're going to find out what g of -2 is by plugging in -2 in for our exponent of x. All right, and what can we do with this? Once we have this here, I can go ahead and rewrite that 1/2 as 2 to the -1st power raised to the -2 power, which gives me 2 squared, which is 4, people. Okay, if you plug in -1 next into the g function, you'll have 1/2 raised to the -1st power. Well, this once again is going to be 2 to the -1st raised to the -1st power, which is going to be 2 to the 1st power, which is 2. Then we'll be plugging in 0 into the g function. You'll have 1/2 raised to the 0 power. That gives you a result of 1. Then you'll have g of 1, which is going to be 1/2 raised to the 1st power. Well, that's just 1/2. And then finally, you have g of 2, which is going to be 1/2 squared. Well, 1/2 times 1/2 gives you 1/4. And so this is how we're going about calculating the y values after you choose what your x values are. Okay, so just keep that in mind. And let's move on to our following page where we're ready to graph. Notice that I went ahead and I carried over our XY chart from the previous page. It's right here, guys, on the left. And we have already identified the horizontal asymptote to be y equals 0. Once again, our domain is going to be from -infinity to +infinity. In other words, all real numbers. And our next step is to graph the horizontal asymptote. Once again, I'm using a dashed line across the x-axis because as long as we have the function in this form, the x-axis is going to be the horizontal asymptote. So that's why I have that dashed line across the x-axis. Next, I'll be plotting our points here. We'll begin at -2, +4. That's going to give us a point right here. Then you have a point at -1, 2. Will be right here. 0, 1. That'll be a point right there. Then we have a point at 1, 1/2. We're right there. Then you have a point at 2, 1/4. That's going to give you a point right here, people. So now graphing this, you'll end up with the following graph, people. All right. It's going to look just like this. Okay, so remember, due to the horizontal asymptote, you're going to be increasingly getting closer to 0, but never ever touching it, right? So that's what we're showing here. And if you want a more fleshed out graph, you can always create more points. But for me, 5 is enough. Yeah, 5 is enough. And based on our graph, it is going to be easy for me to identify the range, which is going to be from 0 to +infinity. So notice that even though this graph is decreasing, it did not change the range nor the domain of our previous problem. Yeah, it's still going to have a floor of 0, right? Not equal to 0, but approaching 0. And it's going to have a high point at +infinity. Yeah. And so let's go ahead and red box it. That's right, guys. So we have our domain, our range, and our horizontal asymptote. If they should need that information, we got it ready for them. All right, so there you go, guys. I hope you enjoyed problem number 2. Next up, I wanted to discuss the expanded form. And the reason why this expanded form may be valuable to you is because it's going to discuss what happens when transformations, translations, reflections, and shifts are applied to your parent function. So that also means that no longer is it guaranteed that you're going to have a point going through 0, 1. Because of the various transformations that you may find in these following problems, then that's going to definitely move the function in such a way that you may or may not be going through that point 0, 1. So that's no longer a definite situation. So that means that that's no longer a guaranteed point on your graph, okay? And with our expanded form, you want to focus on the A, the B, the C, and the D values. And what you see before you is what happens when those values change, all right? So for instance, if A is negative, there will be a reflection across the x-axis. If the absolute value of B is greater than 1, for instance, you'll end up with a horizontal shrink. And it continues with what happens with your C value. Your C value is your horizontal shift. The D value is your vertical shift. And what I mean by shift is the following. The C value will literally move the graph left or right, people. And your D value, it'll move your graph up and down. And just keep in mind that from this point forward, your horizontal asymptote will take on the form of y equals to your D value. In other words, that vertical shift is moving that horizontal asymptote of the graph. All right. So what I have before you is problem number 3. And the first thing you should notice is Mr. Whitt. And I'll be like, what? Well, isn't this the problem that we did before? And you would be correct. You would be absolutely correct. This is the exact same problem we did as number 2. However, I wanted to show you a different approach, people. And that is, we could rewrite this problem as 2 to the negative first power, which simplifies to give you 2 to the negative x. Well, with this 2 to the negative x format, guys, your B value is negative 1. Your B value is negative 1. And what do we say about the B value? If the B value is negative, it's going to reflect the graph across the y-axis. And so the transformation map that I'm proposing is that for every original point in your parent function, all you need to do to come up with the new function's graph is to change the sign on the x value. Yep. All right. And also a little tip about the transformations that I gave you in the previous pages, guys, is that anytime it says horizontal, that's going to adjust the x value. And for any time it says vertical, that's going to adjust the y value. So the B value, that's going to provide us with a horizontal reflection. Whereas if it was the A value being negative, that would have been a vertical reflection. So in order to come up with my new points, guys, all I need to do is simply to change the sign on all of the x values. So I'm going to have a positive 2, a positive 1, 0, negative 1, and negative 2, while your y values remain the same. So we'll bring over 1/4, 1/2, 1, 2, and 4. So that's what we have for our new function of x. So this technique of graphing it utilizes the transformations in order to create a new xy chart from your parent function, which was 2 to the x. Okay, so I'm going back to that original f function of 2 to the x power and using that as my basic function, my parent function, to generate the function g here. Because notice at the end, we ended up with that same base of b, which was 2. All right, so let's continue. So now we should be prepared to graph. So on the left, you have your points from your original parent function, which was f of x equals to 2 to the x. And on the right, you have your new transform function of g of x, which is 2 to the negative x. So what we'll do here is we're going to focus on the right side in graphing g of x, because that's what we're here to do for this problem. And as a reminder, your domain was negative infinity to positive infinity. Once again, we could have plugged in any value that we wanted for x. There was no restrictions on that. And as far as your graph is concerned, notice the format of the function. Your horizontal asymptote is still going to be y equals to 0. It's still the x-axis, just like that. And now that we have our points generated on the right, we'll go ahead and plot those. We had a point at negative 2, 4, so that feels familiar. We have negative 1, 2. We have 0, 1. We also have 1, 1/2. That's here. And we have 2, 1/4. That'll be here. So then you'll connect everything and end up with the following graph, people. All right. So once again, we have our graph of g of x, which was originally written as 1/2 to the x, which is identical to the graph of 2 to the negative x, right? So I showed you this alternative method of graphing that function using transformations of the parent function. Based on our graph, we can once again confirm that our range is from 0 to positive infinity. Red box it. We have our domain, the range, and the horizontal asymptote, everything that you need. And as far as the graph is concerned, once again, this graph is decreasing as the values of y get smaller as the values of x get larger. All right. So there you have it, guys. That was problem number 3. Moving on, I would like to remind you guys that you can set up a paid online tutorial today with me, Mr. Whitt, and Fort Bend Tutoring, guys. So if you prefer my style of tutoring, if you like the way I approach different math concepts, then you and I can work on your math concepts together and your math problems and get you prepared for your upcoming assessments by setting up a paid online tutorial with me, and you and I will go toe-to-toe with those math problems, okay, guys? I look forward to it. So check us out at fortbendtutoring.com. All right, moving on. Here we have problem number 4. So this is going to be our first example where there are going to be multiple transformations involved. In fact, we can rewrite the problem as -2 to the 2 times the quantity of x plus 3. And with this rewrite, you should be able to tell that your a value is -1, which means that there's going to be a vertical reflection. In other words, a reflection across the x-axis. That your b value is going to be 2, which means that you're going to have a horizontal shrink with a scale factor of 1/2. In order to find out that scale factor, guys, you just need to find the reciprocal of the absolute value of b. So taking the value of 2 and then finding the reciprocal of it, you get 1/2, which is the scale factor for that horizontal shrink. And your c value is going to be -3. Recall that your c value is found by finding out the opposite value of what's inside of the parentheses. So notice that we have x plus 3 inside the parentheses in the exponent. You want to take the opposite value, so that'll be -3. So that lets you know that you'll have a horizontal shift 3 units to the left of where this graph would normally be. So identifying my A, my B, and my C values helps me to identify the types of transformations that are occurring here. If you're one of those people that are curious about the D value, that D value would equal to 0 because we don't have an additional constant here adding to or subtracting from our initial expression that we have. So your D value is 0, which means there's no vertical shift, which means your horizontal asymptote will remain at y equal to 0. According to our transformation map, I'm going to say that for every original point, we're going to have the following transformation. That the x values are going to be half of what they normally would be, and you would want to subtract 3 from them. And as far as the y values are concerned, we want to find out the opposite of that y value because of the vertical reflection. So the vertical reflection means an opposite y value. And as far as the horizontal shrink is concerned, you'll need the reciprocal of the absolute value of b, which is going to be 1/2, to multiply times your value of x. And then because of the horizontal shift, you'll be subtracting 3 from it. So that transformation map encompasses all of the transformations that you'll have in this problem. Because of that, that means that you'll end up with the following x values. You'll take -2, for instance, take half of that, which is -1, and then -1 minus 3 will give you -4. Doing that to each of the x values that you have in the original parent function. In other words, for instance, taking half of -1, which is -1/2, and then subtracting 3, you'll have -3.5. All right, so what I'm doing here is I'm taking these original x values and plugging them into this expression right here in my transformation map. All right, so after plugging the next one in, you'll end up with -3, then you'll have -2.5, then you'll also have -2 as the 5th x value after you plugged in 2, took half of that value to get 1, and then subtracted 3 to get -2. Your y values, in order to get the results of those, all you'll need to do is change the sign on your original y values, right? So what do we say needs to happen? We just simply need to find the opposite of each of these values. So you'll end up with -1/4, -1/2, -1, -2, and -4. And these are going to be the points you can use to graph your transform parent function that gives you the result of -2 to the 2x plus 6. So Once again, because we have the same format as before, your horizontal asymptote remains at y equals 0. So plotting that out, I'm going to be using a dashed line to represent the horizontal asymptote. Okay, and it is a line, so you can put arrows on it. No harm there. Then plotting our points of f of x, which is here, by the way, guys, because over here is the parent function. We'll be plotting the points on the right, guys. Remember, we used the points on the left to generate the points on the right using our transformation map. So f of x will have points at -4 and -1/4. And -1/4 will be about right here. Then plotting -3.5 and -1/2, you'll have 1, 2, 3.5, then down a half. Give us a point about right here. And then you'll have a point at -3, -1. Well, 1, 2, 3 to the left, and then down 1 gives you a point right here. The next point is at -2.5, 1, 2.5, and then down 2 gives you a point right here. And then our next point is going to be at -2, -4. So 2 to the left and then down 4. 1, 2, 3, 4 to give us a point right here. So notice, because of our horizontal shrink, that this forced the graph to decrease faster in this case. Another tip to point out is the fact that we had reflected our graph across the x-axis. Going ahead and connecting our points here, you'll end up with a graph that looks like this. There you go, guys. So this is the graph of our exponential function after those 3 transformations. Recall what happened. We had a reflection across the x-axis. We shifted the graph 3 units to the left, so notice how it's been shifted over. And also, there is a horizontal shrink. It's been compacted horizontally, which forced the graph to decrease faster than it normally would. And pointing out your domain and range, we have a domain that is -infinity to +infinity because there are 0 restrictions preventing you from plugging in any value that you wish into the function. And according to our graph here, your graph of the range is going to be from -infinity to 0, all right, not including 0. So your lowest point on this particular graph is -infinity, and the highest point in the graph is approaching 0, not including 0, which is why you use parentheses. Red, box it. We have a horizontal asymptote of y equals 0. We have a domain of -infinity to +infinity. We have a range of -infinity to 0, people. And this completes problem number 4. Moving along, we have problem number 5, guys. In problem number 5, we have f of x equals to 4 times the base of 2 raised to the -x power minus 3. So once again, we will have several transformations involved in here. But first, I want to show you a little something. If you pay attention to that value of 4 that's multiplying on that 2 to the -x, you should also be able to recognize that it can also be written with a base of 2. For instance, we could say that 4 is equivalent to 2 to the 2nd power times 2 to the -x minus 3. Well, because we are multiplying like bases, with like bases, the exponents will add. So you'll end up with 2 raised to the -x plus 2 minus 3. After factoring out a negative in your exponent, you'll have 2 to the negative quantity of x minus 2 minus 3. And with that, we can identify our A, B, C, and D values here. Because we no longer have a coefficient in front of our base of 2, your A value is 1. Your B value is going to be -1. And your C value here is +2. Remember, the values inside of the parentheses, you want to find out the opposite of those, okay? And then the D value here, you will have a vertical shift of -3. So that means that the graph will be moved down 3 units. That's going to adjust the horizontal asymptote. Remember, the horizontal asymptote is going to be in the format of y equals to D. That means in this case, it's going to be y equals -3. So this is going to be the equation of your horizontal asymptote. Notice how it's not y equals 0 in this case for the first time, I believe, right? So we'll come up with a transformation map based on the transformations that are occurring. So to spell those out for you, we'll definitely have a reflection across the y-axis, a horizontal reflection. You're going to have a horizontal shift 2 units to the right, and you're going to have a vertical shift 3 units down. All right. So we'll say, because of that, for all of the original points on the graph, our new function, you'll have to do the following to the x values. you're going to need to find the opposite of that x value, and then you're going to need to add 2 to it. And then you're going to take that original y value that you had, and you're going to subtract 3 from that. So it's going to be y minus 3. And so this is going to be the transformation map that is necessary to generate the new x and y values of our function f. So according to our transformation map, you're going to take each of our original x values, you're going to find the opposite of that, then add 2. So for instance, with -2, you're going to end up with a +2, then add 2 to get +4. So we now have a value of 4 here. Then finding the opposite of -1, that's 1, and then 1 plus 2 is 3. Find the opposite of 0, well, that's still 0, and 0 plus 2 is 2. Then, taking the opposite of 1, that's -1, and -1 plus 2 gives you +1. And then finally, you'll have the opposite of 2, which is -2, and then -2 plus 2 is 0. We'll squeeze it in right there. So, the y values, what needs to happen with those? For all of the y values, you're going to need to subtract 3 from those original values. So, focusing in on our y values here, I'm going to have 1/4 minus 3. That gives me a result of -2 3/4. Then 1/2 minus 3, that's going to give me a result of -2 1/2. You'll next have 1 minus 3, that's -2. Next, you'll have 2 minus 3, that gives you -1. And then finally, you'll have 4 minus 3, which is +1. And so we now have all 5 points that we need to graph our function for number 5. All right. So notice at the top, we have our rewritten f function. And of course, on the right, that's where we're going to be graphing our points for our function f of x. Recall that on the left, this is the parent function's point, just for comparison, all right? And sometimes you'll find they'll want you to graph the parent function as well as the transform function on the same graph. So I think I'll give you an example of that in this problem right here. So for instance, we'll say that our horizontal asymptote is going to be at y equals to -3. So that's a horizontal line at -3, going through -3 on the y-axis here. There you go. And we'll go ahead and set it up with arrows on both ends. And then from there, we'll go ahead and plot our points. So we have a point at 4, -2 3/4, 1, 2, 3, 4. And then we'll go down to -2 3/4, 1, 2, and then almost to -3. All right, we'll put a point there. And then you'll have a point at 3 and -2 1/2. So 1, 2, 3 to the right, and then down 2 1/2. 1, 2, and then a half is here. Then you'll have 2, -2. 1, 2 to the right, then down 2. Then what you'll have is going to be at 1, -1. 1, -1 is here. And then you'll have a point at 0, 1. So 0, 1, that gives you a point here. Okay? So with that, you'll have the following graph, just like this, people. Okay? So that is your graph of f of x. As promised, let's go ahead and show our parent function on the same exact graph, okay? So remember, the answer, the graph of this problem number 5 is in red on the graph here. But I'm also going to graph the parent function just so you'll see those transformations in play. So you'll have a horizontal asymptote going through the x-axis. That's going to be here. All right. And then I'll be plotting the points from the original parent function. That's going to be at -2 1/4. That'll be a point right here. Then you'll have a point at -1 1/2. That'll give you a point here. You have a point at 0, 1. That's going to be right here. And then you'll have a point at 1, 2. Gets us here. And then at 2, 4. That goes right here. So we'll show what that function in blue looks like in comparison to our function for number 5. All right. So in blue is your f of x function. All right. Capital F of x. And in red, you have your new function, the lowercase f of x. So the new function is in red. The original function is in blue, people. So notice the 3 things that occurred. We had a vertical shift down 3. So you can clearly see that the graph was moved down 3 units, right? Then in addition to that, it was moved to the right 2 units. So notice how it's been shifted over to the right 2 places. In addition to that, it's been reflected across the y-axis. So notice from your original function, it was flipped across that y-axis to end up with the new form that we have now. So notice that originally it was increasing, but after that flip across the y-axis, it is now decreasing. In other words, the y values are getting smaller as your x values are increasing. So with this, we want to show that our domain of the function was negative infinity to positive infinity. We can see that because of all the arrows going to the extreme left and right. And then your range of the function, and remember this is for our new function of f of x, the lowercase f of x, that the lowest value that it's approaching is -3, not including -3, and then the highest value is approaching positive infinity. Red, box it. Here your horizontal asymptote is y equals -3. Your domain, guys, is all real numbers from negative infinity to positive infinity, and then the range of the function is from -3 to positive infinity. And done, people. That was problem number 5. So I hope you got a lot of great information from this example here, guys. I felt really good about that, right? Let's move on. Here we have problem number 6. And in number 6, we have h of x, guys. And h of x equals to 1/2 times 3 raised to the x minus 1 plus 4. So this problem is different from the other problems because it has a different parent function. In fact, if you wanted to define the parent function, you would say that that parent function would be 3 to the x. And because of that new parent function of 3 to the x, I've given you a new xy chart to represent that new function of h of x equals to 3 to the x. The lowercase h of x is going to be dealing with our new function that we have in problem number 6 after all of the transformations have occurred. What values do we need to identify those transformations? Well, for one, you can identify that your a value is 1/2, that your b value is 1, your c value is positive 1, and your d value is positive 4. What does that mean for us? That means that there's going to be a vertical shrink with a scale factor of 1/2. When you're looking for the scale factor based on your a values, the vertical scale factors, it's always going to be the absolute value of a, okay? Then, because we don't have any coefficients other than 1 in front of our variable x here, your b value is 1. Your c value is going to be positive 1 because it's going to be the opposite value that you see there. And then, of course, there is that plus 4, which means that the graph was going to be moved up 4 units because of the vertical shift of 4 for the value of d. All right. So remember, once again, the horizontal asymptote is always going to be in the form of y equals to your d value. Well, in this case, it should be y equals to 4 because that d value is 4. So your horizontal asymptote is y equals 4 for this problem. Our transformation map is going to be that for all of the original points in the parent function, our new function will have the following adjustments. As far as your x value is concerned, you're only going to need to add 1 to each of those x values. As far as your y value is concerned, you'll need to take half of y, all right, and then add 4 to it on top of that. Okay, so this is going to be how you generate your new values for your new XY chart. So the X values, you'll just need to add 1. The Y values, you take half of the original and then add 4. Starting with the X values from the parent function, you'll just simply add 1 to -2 to get -1. And you'll just simply do that to each and every one of the values that you have for problem number 6. So after plugging in each of the x values into your transformation map, you'll have 0 as the next value, 1, 2, and then 3. For instance, that last value of 2 at the bottom of our x values in the parent function, you'll have 2 plus 1 to give you 3. All right, so it's just simply plugging it into the x plus 1 there. For the y values, you're going to take each y value and then add 4. For instance, with this 1/9, you'll say half of a ninth is 1/18, and then 1/18 plus 4 gives you a result of 4 and 1/18. Just like that, people. 4 and 1/18. I think I could do better with that 8. I want a better 8. Can we make a better 8? Is that? I'm not seeing. There we go. We're going to go with that. I was waiting to see like some space in between the upper and lower part of the 8, you know what I'm saying? Try to define that a little better. That's what we were trying to do, guys. So we have 4/18. You'll do that same process with 1/3. 1/3, taking half of 1/3, you'll get 1/6. 1/6 plus 4, just turn it into 4 and 1/6. Okay? So mixed numbers do help. We can do a better 6, right? There we go with a better 6. And then finally, you'll be plugging in 1. Taking half of 1, that's 1/2. And so you'll end up with 1/2 plus 4, which is 4 and a half. right? You'll continue that process and end up with the following y values for the remaining two. You'll have 5.5, and you'll also end up with 8.5. All right, so these are going to be the y values that you generate. For those that are curious, if you take 9 and then take half of it, it'll be 4.5, and then 4.5 plus 4 gives you 8.5. Okay, so that's how I came up with that. All right, let's go ahead and look at our graph, people. On the left, you have the original h of x, xy chart, and on the right you have our new function, the lowercase h of x. All right, so I'm just going to graph the function on the right this time, guys. So I'm not going to worry about the parent function, or should I? You know what? You're right. Let's graph both, people. All right, let's come up with a color for both of these. We're going to graph our h of x, the parent function. We'll be using blue. Okay, we'll use blue. For the graph of h of x, we'll use red. Okay, that's what we'll do there. There we go. So these are going to be the colors that we use for each one on our graph here, guys. We have already noted that the horizontal asymptote of our new function is going to be y equals to 4. So let's go ahead and graph that. Let's show that. So you go up 1, 2, 3, 4, and you'll have that horizontal line going through 4 on the y-axis. All right, putting arrows on both ends. Okay, and then you'll be plotting the points on the right. So we're graphing the lowercase h of x first, guys. So the points that I need to graph are -1 and 4 and 1/18. So that's going to be a little smidgen off 4. Okay, so I move 1 to the left and then up 4 and 1/18. Okay, then at 0 I have 4 and 1/6. So that's just going to be a little bit higher than that at 0. Then at 1 we have 4.5. So that's going to take us here. And then at 2, we're at 5.5. So go up 5.5. That's going to be 5, and then a half is going to be here, right? And then for 3, we're at 8.5. Okay, well, at 3, we have 1, 2, 3, 4, 5, 6, 7, 8.5. That's going to probably be a point right here, guys. Okay, so if I were to graph that in red, by the way, we'll have the following graph, people. Just like that. How cool is that, right? We have our graph. And then for comparison, remember, we're going to be graphing the parent function, which was h of x equals to 3 to the x. For that function, your horizontal asymptote is going to be y equals 0. So that's going to go through the x-axis. So we're going to show the horizontal asymptote there for comparison, right? Okay. And then we're going to also plot the points on the left this time. So plotting those points, we're going to be at -2 and 1/9. -2 and 1/9 is just going to be a little bit off of the 0 mark. Then we're going to be at -1 and 1/3. It's going to take us here. Then you'll have 0, 1, takes you right here. You'll have a point at 1, 3, which takes you here. And then you have a point at 2, 9. So 2, 1, 2, 3, 4, 5, 6, 7, 8. And then what? 9's going to be right here, guys. There you go. And now we want to graph this in blue. Didn't we say that? So graphing in blue, you have the following graph, guys, just like that. Okay, so is that not great for comparison for the transformations, people? And what were those transformations, by the way? We had a vertical shrink of 1/2. Look how slow it took us to rise to even 8.5, guys. From the points that we plotted, we didn't even get to the 9 that occurred at 2. Right? So there was that. It took us a while to start climbing up. Another thing to pay attention to was the fact that our graph was moved slightly over to the right by 1. We slid it over to the right by 1 unit. In addition, we also raised the entire graph up by 4 units because of that vertical shift, that d value being equal to 4. And because of that, let's once again focus on the graph in red as we go ahead and define our domain, which is going to be from -infinity to positive infinity. There was no restrictions on this graph. You have points going to the extreme left and the extreme right. Then the lowest value on our graph that we're approaching is +4, not including 4. And then the highest value is positive infinity. So therefore your range is from 4 to positive infinity. Also notice, guys, that I have a preference of finding out the range at the end. It's much easier to identify that range after you have graphed the function. But for some people, it's not even necessary to graph it. But for me, I like to see it. All right, so that being the case, guys, that completes problem number 6 And that also finalizes the video. That's right, guys. So that was our video on graphing exponential functions. Give us plenty of feedback in the comments section. Go ahead and like the video, share it, please. And also subscribe to the YouTube channel Fort Bend Tutoring if you haven't already. And I want to give a special thank you for making it to the end of this video, safe and sound. And I'm out of here, guys. This has been Mr. Whitt. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.